Hey everyone, I'll show you how to segment cracks, and I mean concrete cracks, using YOLO. Now, what I mean by that is that if you have an image of cracking, as you can see, for example, here, what we want to do is we want to train a YOLO model to input basically the image on the left and be able to output the image on the right. Now, this is a completely random example from an image on Google. This has nothing to do with this website or anything like this. I just wanted to show you this to explain what we're going to be doing. All right, so what are the steps? We're going to follow these steps that I already prepared. The step one is to obtain the data. You want to, of course, have the images that you will use to train the model. Step two, you will also need to prepare the data. We will explain this further later, and then we'll train the model after we have the data. And we'll review the results, see if they're good, see if they're bad. And now for anyone who doesn't know what YOLO is, I will go ahead and show you the official website of YOLO. So it is, I think it is not quite by Analytics Hub. I think they own it. And if you go to the website, let me go ahead and change the language to English so you guys can understand. So if you go to the website of YOLO, you can see here like what it does. Basically, it started as a computer vision only for object detection, and then you can see here that it became also used for segmentation, for pause estimation, for tracking, for classification. It's very diverse and it's a very powerful tool in computer vision. So far there are 12 versions of YOLO, so 12 versions of the models that we will be tweaking today. You can see here every version there is, and we're going to be using the newest one, which is YOLO11. Now, I don't know if you guys know this here, but there's also YOLO12, which is version 12. We're not going to be using this. The reason for that is we want to do crack segmentation. So we want not only to have a box, not only to detect the cracks, to have a box around the cracks, but we want to segment the cracks. We want to have the cracks drawn basically on the images that we give to our model. So here, if we go to this website, you can see the maps, the mean AP scores of different models here. And let me go ahead and show you this right here. So here you have the different models that you can use. Now, keep in mind that there are two versions of these models. One is a version where the model just comes untrained with all of the parameters basically completely random, and the other version of it is to basically have the trained model. Now, these right here are all the trained models, and they were trained on a large dataset. The dataset is called COCO dataset. You can check on the website or online if you want what the COCO dataset has. But it's not really necessary. All you need to know is that it was trained on a very big data set, and it can already detect many objects, or in this case, segment many objects. So we want to do the segmentation here, and therefore we can go to this table right here where it also shows us the performance, and we're going to go to the segmentation. Here you can see the different version of the YOLO models. You can see that there's an N here, which stands for nano, and then there's small, medium, large, extra large. Now, you might ask me what's the different versions are for. And basically, the more, the higher the version, the more the number of parameters. And I think here you can see how many parameters there are. So for the nano model, you're going to have 2.9 million parameters. And as you go up, you'll have more and more parameters. And I don't know if you noticed, but here there's a huge step up in the number of parameters between the large and the X-large models. And you mostly want to use something between small and large. X-large is very heavy and it takes a lot of time to run. Like it runs significantly slower than the other ones. Not that they are slow, they are actually pretty good compared to other frameworks, but you want to avoid using X-large in many industrial settings, other than when you have something like, you want to detect cancer, or it's a critical mission that you cannot mess up on. in that case, you definitely want to pick the X large one if it's extremely critical. In other industrial settings where you just need to detect concrete cracking on whatever it is, on buildings or walls or bridges, it is completely enough to use the large one. Now here, because this is only a demonstration, I will only be using the nano model. So I'll download this one, and I think I already downloaded it. Let me go ahead and check real quick. So here I have a folder with everything that we'll need in this video, and I'm not sure if I don't. Okay, so there it is. It's right here. Let me go ahead and delete this one. Don't need this one. And this one is a trained model. You just have to download it. Now we have the model. We want to train it using a dataset, so it detects crack pixels. And I will also put this. I will upload everything you see in this folder. Other than this, of course, you don't need the NVIDIA driver for sure. I will upload everything you see here to GitHub, to my repository for YOLO, just so you can see all of the codes and all of the materials that we will use. What you want to do is, I'll also give you the link in the description of the video to this dataset. It's basically just a dataset on Kaggle, which has many different datasets, and I'll also provide the link in the description. Now you can see here the characteristics of the dataset. It has images of 448 by 448, which shows, it is not that important. Of course, preferably you want to have something 640 by 640. But again, since we're only doing a test here, and I'm not really expecting the best results in the world, and this is only like a tutorial, we don't really need to have the best quality images. And let me go ahead and download this dataset right here. All right, so finally it has finished downloading, and if we go here to the folder where I downloaded it, we can see it. And what I'll do here is I'll extract all of the dataset right here in this folder. Okay, so it finished extracting. If we go ahead and open this folder, you can see here that it has images. We don't really care that much what it has exactly, as long as it has the images. Okay, it has the images. And we have a folder for the masks. We also have test and train sets. And so we can see the dataset is already split into, I'm assuming these ones are, no, they're not for the training. I'm not really sure what's going on here, but basically we're going to assume that you only have the images and the masks. So I'll go ahead, read me. I'll not read it. Don't do that, by the way. Like you wanna get as much information as possible. But since this is a demo and we don't really care that much about the results anyway, we're not really, realistically, we're not gonna get something like amazing. Okay, this is just a random dataset that we are going to use. So yeah. Now let me go ahead and show you how in a realistic setting what you will have. You'll basically have the images and the masks. So the images are, let's say we have this image, and what the masks are. Okay, so the images are basically the images, and the masks are these masks right here. So as you guys can see, the masks are basically annotations on, and this is not a slideshow. Can you go back, please? Okay, it doesn't go back. Let me bring you back to the image. But yeah, as you guys can see, it is basically the annotation of where the crack is. Okay, now the important part, the images. Okay. To train the model, we cannot simply use the images and the masks like this. Okay. The masks have to be converted into text files. And the images, you can keep them like this. But what YOLO does is, let me open Paint here. What YOLO does is that if you input an image, let's say this is your input image, and let's say it's 400 by 400. What YOLO does when you input it, YOLO will resize it to 640 by 640. Okay, Now this is nice, but it comes with its restrictions. When you resize the image, or in this case, when YOLO resizes the image, the quality of the image will be degraded. And we don't want that. We want the quality to be as good as possible, especially with such images. You can see here the image's resolution is 448 by 448, which is obviously not the best quality. So we don't want YOLO to resize the images to 640 by 640 because that will only decrease the quality. And a solution to that is to basically what we'll do, let me explain this here. Instead of resizing the image like here, we will add padding around the image. Okay, so we'll make the image 640 by 640 by just adding a black frame around the image. Now, YOLO, when it has black frames, it is usually something acceptable. So how can we do that? How can we expand the images into 640 by 640 images with padding? I have this code right here, and what I have in this code is that it takes in a folder of the images and the folder of the masks. And what it will do is it will change the images, it will add the padding to the images, and it will also add the padding to the masks. So I will make another folder here called images with padding, and I'll also make, let me correct this one, with padding. And the other folder, it will be called images with, masks with padding, basically. So let me change this one. Okay, now we are ready. And we're going to input here the folder with the images. I think that's already the correct folder because I've already done this once before, but it all was okay. This is the right folder. So I've already done this once before and I lost the video. Unfortunately, that's why I have to record it all over again, which is painful, but you know, okay, it is just painful. There's nothing more to it. All right. So we have the images, we have the masks, and the output folders. Okay, let me change these two. I named them something else before. So this is the output folder, and this is the output folder for the masks. Okay, save it, run it, and it's working. And if we go to the folder now, there's nothing. Why is there nothing? What is happening? Is it overwriting? Images and masks, and it's saving them here. All right, so apparently I had different passes. These are the correct passes. Okay, so whatever, when you do it, you will enter the the correct passes. You will not be like me. Let me go ahead and delete these. Oh, not this one. Okay, we will restore the one we just deleted because that's the one we need. We will delete this one. And these are the actual folders that were created. So what happened here was I basically inputted wrong passes, but of course you need to input the right ones so they get stored where you want. All right, so now we have the images, we have their mask, and we have the images that are padded. You can see them right here. This is basically a padded image, 640 by 640, which is wonderful, and this is how it looks like. And if we go to the mask, we can see that they are not this one. Oops. If we go here, you can see that they are now padded with a black padding, a black frame. Now what comes, we basically obtained the data and we need to prepare it further. And how do we do more preparation? Now, just a side note, you don't really have to resize the images to 640 by 640 for the whole training to work. This is something as a bonus that we did to make the training process better. So it is not really a must. All right, so now the data preparation, which we already did some part of, we will need to do the following, okay? We will take, now this is kind of confusing here, we have 4 folders. I'll delete these 2 because we don't really need them anymore. We will work with the ones with padding in a realistic setting. You do not want to do what I did right now. You want to keep a copy of everything. Keep a copy, keep backup everywhere, even on a different PC, on a different server if needed. All right, so now that we have the images and the masks with padding, what we are going to do is we basically want to add the structure right here. Okay, we want a folder with the images, we want a folder with the labels, and we want to split them into 3 sets, a training set, a validation set, and a test set. The test set is optional, but I will do it anyway here. And the ratios, as a rule of thumb, you want to have 10% of your data as a training set, 10% as validation, and 10% for testing. Now, this is what usually most people do, but feel free to change them and maybe you'll discover something new. You never know. The labels have to be in a text format, okay? These have to be text files. So the labels, which are here's the masks, have to be converted into text files. How do we do this? We go to one of my codes here, which is let me see, black masks to text. I'll open the script. So this is basically a script, and all it does is that it will convert the padded masks into text files. Now for this to work, we need to input the folder with the masks, and we also need to input the folder where we want the text files. Now let me go again to our 2 folders, and here I'm going to create a new folder and I'll call it text, okay, just simply text. So I will copy this link or this path right here to tell it which folder we want to input, and this is where the output should be saved. I will also tell it to output everything here, save it, and what you can see here is that you can change these 2 values depending on what kind of images, what kind of color you have. This is basically the threshold of how black it has, or how this is a grayscale basically of how white the pixels have to be in order for them to be considered as crux. Feel free to also leave it as default if you have similar masks as in this case. Here you can also see the class ID, and I'll show you what this is in a moment. So let me save this and run it. So it is converting them, and let's see this one for example. And what this is a text file with, I'll zoom out of it so you can understand it more, with the instances. So from an image, it can construct the instances. I'm kind of speaking like an AI at this point, but let me explain in human words. This right here is a class index. This basically means that you have a crack here, okay? And it doesn't, of course, know that it's a crack, but it knows that it is 0. It's a 0, it's something called a 0. It's a class ID, basically, just an ID identifier to what kind of segmentation we're doing. So it starts with a 0, the text file, and this means that we have like a 0 thingy, which is a crack here, and here it has until here. Okay, so all of this is supposed to be one line. All of this is basically X and Y coordinates to a polygon that will draw this crack right here, or this instance. And this one is an instance followed by X and Y coordinates of the crack. And you can see that all of the coordinates are normalized. These are basically the text files that we should have. Now, what you want to do here is these are just text files. And how can you know if you messed up at some point or if you did a good job? So what we will do is we will go to the script right here. It's called visualize YAML text on images. And it is basically like the name says, all it does that is it takes, I'm not sure anymore if it's for folders. It is for folders. So all it does is that it takes the text files and it draws them onto the images. So we make sure that we did a good job. So let's go ahead and see if we actually did a good job. I will go ahead and make this folder and I'll call it tests text. I'll put only the first 3 and I will put the first 3 images in another folder that I will call test images. All right, so now we're gonna take the path of this folder of the test images. We will put it here, so the image folder, and we will also take the text folder and we will input the path right here, the annotation folder. For the output, I'll honestly just output it right here because it's basically just a small test we're doing, and I will delete everything once the test finishes. So save the file, of course, run it, and I'm saving using Control Save. Now, if we go to the folder, we can see that it drew the cracks. So, for example, in the text files that I showed you, you can see that these are basically 2 cracks. You can see the first crack goes from the left to all the way here, and this is the other crack, and that's why we had 2 lines basically in the text file, because there were 2 instances. An instance is basically one of these shapes, one of these polygons right here. And it is not a problem that they are not filled, because everything that is inside the polygon is considered a crack basically. So here we can also see that it did a good job highlighting the cracks also right here. Now that we confirmed that we did a good job, I'll go ahead and delete all of these because we don't need them anymore. Oops, I deleted the wrong folder again. See, that's why you want to have backups. All right, let's see. So we want to delete this one. We'll delete these 3 and we'll delete the test image. And now the text one is all we need, and we also have the math with padding. Now I could delete this one, okay, but I will keep it just in case we need something data from it. Okay, so now we will take these and the text files and we will make them into this structure right here. Okay, so we will have the images in a folder called images, and we will split the images into 80% training set, 10% for validation, 10% for testing. And we will also take the text files, only the text files, not the math, and we will put them in also respective folders with the same ratios. We will also make a YAML file to have some data about the dataset. All right, so how do we do this? We will go to the folder right here, and again, I'll be uploading everything, and we will go to Dataset Splitter. Okay, so we will open it, and what this does is that you can say here how many of the images you want to be in the, like how much the training ratio should be, how much the validation ratio should be, and the test ratio. Now, before I continue, there's something I need to also show you. There is this one right here, the filter and split code. And what this does is that, if we go to our dataset right now, let me show you, why do we have this? Okay, let me show you the images here. If we go to the images here, you can see that there are too many images that are cracks. There are some images that are not cracks, like this one right here, or maybe there's like a small crack here, but there are images with cracks, there are images with no cracks. And usually what you want to do is you want to have 50% of the images being this thing that you are segmenting, in this case cracks, and 50% of images without cracks. So here I will skip this step because the data set is very limited. It's not the best data set, and we're not going for like award-winning results here. We're only doing a tutorial, a test to see how this works. So I'll keep them as they are. But it is important that you have, by the way, you can use this code right here to split the data set. Here you have the instructions, so it shouldn't be a problem. But yeah, as I said, it's important that you have a variety of different conditions of the cracks, if that makes sense. All right, so now let's go ahead and continue where we left. In the dataset splitter, we will, let me see here, images with padding. So we want to take these images, we will input the images folder here. And we also want text files. These are the text files right here. For the output folder, I will create a folder right here called TD. It stands for test dataset, and I will place the results here. All right, save it, Control S, and run it. Now this is running, and it already created the folder as they are, and now it's placing all of the folders that we need in these folders. Now this one is empty because it started with a training set, and if we go here now, this one is kind of full. The data set is not really that big, so it finished almost right away. All right, so now we have the images and the labels, and as you guys can see here, this text file. Now what is missing is the YAML file. All right, so I actually downloaded this one right here from another one of my projects just so we can use it. So this is an example file of a YAML file. And I'm going to go ahead and place it here, and we're gonna open it so you guys see how it looks like. Nothing really complicated, as you guys can see. We need the path, so this should be the path of the dataset. So YOLO will know where the dataset is stored. And then here you can feel free to leave this as they are. These will basically tell YOLO where all of the images are placed. Now, as for the names, it's kind of obvious at this point. This is what you can call the class identifiers that you have. So in the text files, there were zeros, and here you can tell YOLO what to name these instances. And here we have 0, double points crack. So we want to just name these class IDs as cracks. You can of course name them something else, but we don't want a confusing name. If you have multiple instances, you will need to do the following. 0 is for crack, 1 is for something else, and so on. Of course, you'll also need to run the script that converts the masks into text files multiple times, and you will need to change the class ID. So now we will save this file right here, and we will have our dataset basically ready. Now we have the dataset ready, and we are ready to move on to the next step. Step 3 is to train the YOLO model. Finally, we have the dataset ready, and we can train the model. Now, this is the model that we have, but how the hell do we train it? So what we will do is, this is another one of my codes. We will open it, and let me see. I'll actually close this one as I already opened it and open it back again. So here we have some information about the structure, how it should look. And here we have some information about a training run. Here we also have some, this is also for videos if you want to work for video, but we don't want to really work with videos here, and I'll just show you the segment of the code that we will use. Now, of course, as you guys can see, this is a Jupyter notebook. It's basically in the form of a Jupyter notebook, and I already have, you can see here, I'm using Python 3.12.4, and this is from a virtual environment, basically. So it's a Jupyter notebook running on a virtual environment. Now, why a virtual environment? Because I wanted to use the GPU because I didn't want the training to last so long, and I haven't used this PC for programming before. So obviously I need the CUDA drivers to be able to use the GPU, and I had some trouble. That's why I created the virtual environment. By the way, you will also have many problems probably with libraries and many small things that you will not be able to enable right away. With the CUDA drivers, they are a huge pain to install and get to work. And that is completely fine. Just keep working at it and you will get there. Ask ChatGPT and just keep going, keep trying different things, and you will get there eventually. It is definitely time consuming, as these small things do actually take many hours to fix and repair in many cases. But yeah, hopefully you already have everything ready to go. All of the libraries and all of the drivers that you need. Now, I'll not show you how to do everything here, how to create like a virtual environment and how to run this Jupyter notebook on a virtual environment, because you don't really need to do the same as me. And it also will take me forever to explain everything in like huge details. These are basically like kind of some of the things that you already need to have some information about. So this is the functions that we will be using to do the training. It is basically the training function, and here we need to input. First, we need to input the model right here. And let's see. So the model is this one that we'll be using. I'll just go ahead and copy this path. And here we have the right name already. So this is already. And here we also have the path for the YAML, file. So let me go ahead and copy this. I think it is the same. No, it's not the same. td/td.yaml. This is example YAML. So let's actually change the name to td, so it fits with this right here. All right. So now we have everything ready. Here it says 50 epochs, and you can definitely do more than 50 epochs. Usually what you want to do is you want to do 100 to like 150, maybe 200. But it all depends on the dataset and what you are doing and what kind of results that you want. As for the batch side, this is directly related to the VRAM of your GPU. That if you are using the GPU, and you should use the GPU by installing CUDA drivers. Yeah, but this depends on how much VRAM you have in your GPU. Mine is an RTX 2070 Super, and it has 8 gigabytes, and I'm using a batch size of 32. If you have like 12 gigabyte, it will be kind of close, but you can try 64. If you run into any problems, you can go back to 32. But of course, the more, the better. Here you can also see the image side. Yeah, the optimizer, it's by default on Atom. You can change it to something other than Atom, but usually what you want to use is Atom. Defies equals 0. 0 is for the GPU. You can also, if you have multiple GPUs, you can use one. And if you want to use the CPU, what you have to do is just write CPU right here. Okay. Well, we don't want to do that. we want to use the GPU, so I'll leave this to 0. And here save equals true. This means that it will save the results of the training and not only the model. Save period, it will save it every 5 epochs. So every 5 epochs, it will create a version of the fine-tuned model that we have. Now, this is called fine-tuning. By the way, it's called fine-tuning because we are not really training the model from scratch, but the model is pre-trained and we are changing some of the parameters so it can detect crunks. And therefore, it is called fine-tuning. Number of workers, this also depends on the kind of GPU that you have. You can leave it to 4 at 4. It shouldn't be a problem. Pre-trained equals true. This basically means what I said now, that it is a pre-trained model that we are working with and it is not initialized completely from scratch. All right, so now we have everything ready here. Let's go ahead and save it and you will run it. So when running, and hopefully it runs smoothly here with no problems. Here it's showing us the Python version that it's running at and the Torch version. It's also showing the GPU that it is using. It's also here it's showing the parameters, or these are called the hyperparameters that are being used. They are these right here. There are more hyperparameters. Feel free to explore more. And of course, these hyperparameters do affect the training results. So the kind of optimizer that you are using does influence the training results. Depending on what kind of optimizer you have, you will have different results. So if we go down here, you can see that it is here. It's already started to train and it's using 6.3 gigabytes of memory out of 8 gigabytes of memory in the GPU. And it started with epoch 1. Here you can see the progress. Here you can see the image size. And you can see the number of instances that it is in a batch. Here you can also see the segmentation loss. This is what we are basically interested in. There is a box loss, which we are not really interested in because here we are doing segmentation. We're also not interested in these. But we want to focus on the segmentation loss. And as you train the model, it will become less and less the segmentation loss. And of course, you want to have it as small as possible. The smaller, the better. And this is usually a good indication of how many epochs you should train your model for. So if you see that if you train your model for like 100 epochs and the segmentation loss is like 0.5, and if you train it for 200 epochs and it becomes 0.49, then it is obvious that you're not going anywhere by training the model for more epochs. So this should be completely ready. Now we have here 4 more percent, 3%, and when it finishes, it will start with, so you can see here we are at 3 almost, and now it is saving the results right here. Now it started with the next epoch, and you can see the segmentation loss, it keeps going down. Now I don't want to sit here for like 1 or 2 hours to show you what will happen at the end, because nothing really will happen. You will just complete the training, and I will stop it here because I already trained it. Okay, let me stop it. I already trained it. Now, of course, depending on the model that you have, if you have small, you will need more than nano. Okay, so if the nano training takes 2 hours, the small will take 4 hours. The large one will take you like 8-10 hours. Of course, this depends on what GPU you are using, but the more complicated, the more parameters that you have, the longer it will take for the model to finish. And this does affect also which model you are using. This does affect how fast it will run the inference at the end, how fast it will be able to predict or just draw the cracks from a completely empty image. So let's see, when you are finished, you will have a folder called runs. So if we go here, it says segment, and the correct one is train 3 here. I already had some trouble training the model and I fixed them. That is why they are, this is train 3. So if I click it again, try to train it, it will be train 1, train 2, train 3, but this is what you will get at the end. It will be called the train for you, basically, okay? So here you have the results. You can see them. This is a confidence curve, which here it clearly doesn't look too good. The F1 score, which is here's the y-axis, you want to have it much more than this. But because this is a completely random data set that isn't really too good, we're not really expecting the best results here. The confidence score is basically how confident the model is that it is detecting cracks. And you can see here what is interesting is, because we only did 50 epochs, you can see that the model is like, it has many mixed confidences. You know, it is the same, it's completely not sure. It's completely not sure of what it's seeing, basically, because you can see the confidence is like, and the F1 scores are almost the same. Like it's the same F1 score for 0.6, same for 0.2. Here you can also see the precision. Now I'll not explain what everything is. Here we have the confusion matrix normalized, and we can see right away here that the results are basically not the best. All right, we go right. We can see here the different boxes that the different sizes of the instances of the cracks. All right, this is again the confidence, and we have a bunch of more data. Here we can see what is interesting here is this one, the training, the segmentation loss. Actually, the validation set is kind of more important, because you can see here that it approaches 0. So this is basically the numbers that I was showing you. And you, of course, wanted to approach 0. Or here you can see some examples of the training batches that it used. All right, so now let's go ahead and test our model. Now, these results are kind of obvious that it is not performing well, but we are still gonna go ahead and see how it actually looks. And for that, I'll just Google concrete cracking. I'll not download a dataset, but let's see how good it performs. Let's take this image right here, for example, and download it. I'll download it and I'll make a folder here called tests. And here I will call the folder test images. I'll say it's here. Let's also save this one. Let's see. So we will save this one to, this one is very complex. I think the model will completely screw up here, but let's see, it's kind of interesting. This one, let's save this one. This one is gonna be hard because it's not really black and white. All right, so these are gonna be enough, and let me just go to the photos that we installed, and I just want to make sure that they are, let me see, JPEG. Okay, this one is WebP. It's JPEG. So what I will do here is I'll delete this one because or you know what, I'll keep it and show you what you can do to make the code works for even different formats of photos. So here we can finally go to predict. So this one right here is for prediction. It will basically, it's called prediction, but it's more like drawing and saying which pixels it thinks belong to cracks. Now here you can see that it works with these formats, but we also want to add one of the images was JPEG like this, and we want to add this format right here. And we will also add WebP, okay, just to make sure that it's written correctly. And yeah, it is actually a small w, so we don't want to mess up on that. Let's not forget the dot. And here I'll just create two other loops. No, not really loops, just statements. I'll change this to this. Feel free to, explore the code, but it will take too much time for me to explain everything. So yeah, let's go ahead and save it. And what we will do for the code is we will also create an output folder. I'll just call it output images. Test images will take the path of the text images. It will take in. Now we need the output folder. What I want to say is that depending, of course, on what kind of images he trains the model on, okay, it will have different results. It's basically like feeding the model, If you feed it good things, it will be happy. If you don't feed it good things, if the annotations are not very accurate, it will be bad. Let's go ahead and see here the models that we have. Okay, so something that I didn't mention is that if we go to this folder, if we go to weights, these are the models that we have. Okay, so these are the trained, fine-tuned models. And it says here, this is the best one, which is the last one. So on the 50th epoch, it was the best. It gave us the best. It gave us the best model, which is not something that you want to have that much. It's very typical, but you want to do more epochs is what I'm trying to say. All right, so we will take best, and I will put it right here. We will call it TD. That's td.pytorch. So all of the models are basically in a PyTorch format. I'm missing the slash. Okay, so let's save it. And something also to note here, if the image size is more than 640 by 640, because YOLO only processes 640 by 640. What this code does is that it will slice the images into multiple slices, and it will process each image, each slice individual. Okay? And what it will do is it will also have an overlap. Now, feel free to also play with these settings, maybe change the slice size, but what you need to do is, what you need to know also is that if I change this one to 800, for example, it will do an 800 by 800 slice. But here's the thing, okay? YOLO just remembers that it resizes everything to 640 by 640. So the 800 by 800 image, means slice, will be resized to 640 by 640, and it might lose some of the quality. Okay, so that's why you most likely just wanted 640. All right, so let's save it and let's run it. And it doesn't work. Why does it not work? Because I basically work in a virtual environment and I forgot to activate the virtual environment. All right, so I had to run a bunch of commands to get it to work, but I'm completely inside my virtual environment where now it should run. And it doesn't run. Okay, so basically what's happening here is that it's not really running on the Python version of the YOLO. of the virtual environment that I created. That's why I will paste a line. So it's this line right here that will run the code from within the virtual environment, which should work now. And it is working. Nice. So you can see here that it's basically chopped down the images into these slices. This is probably the last slice. That's why it's 416 by 640 and it finished. So we don't need the solutions. Let's go and see what kind of results we have. All right, so let's open the first one, and it's not bad. It's not really bad. So something that I want to tell you is, you see the pixels where there is no crack. Basically, all of these are counted in the confusion matrix, and that's why the results are not the best there. So this one, again, if we have a variety of cracks in the data set that we used for the training, if we, for example, have such images in the training data set, there will be no problem detecting the cracks. So let's see this one right here. This one right here, so because the cracks that were, this actually does a pretty decent job, but because the cracks that we used for the training are kind of wider, it is like it is doing this. Basically, it's making the area larger. But this right here is actually impressive. You can see it didn't miss anything. Wow, let's like, this is actually impressive. I was not expecting this. This right here is also very impressive. You can see that it missed some of the places, which is not the best, but it's really doing a good job. Wow. Damn, okay, this one is like a complete mess. Did it even use this one? I think it didn't even like, oh, it did, okay. It's in the output folder. Okay, this one is a complete mess because of how much the damage is. It's not really a crack anymore. But yeah, like these results right here are actually pretty impressive. They are very, very impressive. Now what I will do is I will check one of the models that I trained before, and I will see the results on that model, which I used many data sets to train. I basically used many online data sets to train it, and let me go ahead and grab it real quick. All right, so I grabbed the model that I already trained. I trained this model with a much better data set, and it was 400 epochs. I trained it. It's a large model, and as you can see, you can tell from the size that it is much larger than this nano model right here. So we will also go ahead and use this one just to compare the results and see what we have. So here I'll create another folder, test images, and I'll just call it 2. So, all right, so here we will need to change this to output images 2. And all right, no, this should be output images, sorry. And we will change this to the name of the other node. Let's go ahead and save it, and I'll run it again, and you will see this time that it will take longer basically because it is a large model. Okay, so it actually didn't take that long. Let me just make sure that everything worked correctly, because it really didn't take too long. All right, so let's go ahead and see how the other one performed. And you can see that it does perform very decently. Here you can see that it kind of missed this one, but it's not really a big deal. And let's see this one. This one also looks very good, very nice. Not sure if this one is actually supposed to be a crack, but it's it's very decent. And we'll take a look at the last one, and here it kind of doesn't perform in the best way here, but it's not really a very big problem. So now after I use this one, I kind of want to show you something. So you can see here that you can also change the confidence. So depending on the confidence that you choose here, you will have a different confidence. And this one is a confidence for the smaller images, and this one is for the larger images. So here we are dealing with the larger images than 640 by 640. That's why we can play around with the confidence. And we're gonna try to use the model that we had before. So it's a TD model with low confidence, just to see what kind of results we get. All right, so let's run it and let's see what kind of results we get. Okay, so it's running. And let's go to output images. Sorry, actually, I forgot to change the name of the folder here, so it overwrote the other ones. And let's see what kind of results we have. This looks very decent. Like this is keep in mind we trained it with a completely trash dataset online. This one right here is also not very bad. And this one, ooh, wow. That's actually insane. Okay, this one is a complete mess, but wow. Okay. Those were pretty good. Yeah. They are pretty nice. So as I said, I'll upload everything needed to GitHub, and I will also leave the required links in the description. And if you have any questions, feel free to ask me or contact me.